Ever notice the periodic table's odd shape? It's not a simple grid. There are blocks, towers, and two rows floating at the bottom. That design isn't random. It's a map of all known atoms, showing how elements are related. The table's shape reveals patterns in how elements behave and interact. It's a cheat sheet for the universe, letting us predict how substances combine and react. Scientists like Dmitry Mendeleev discovered that arranging elements by repeating properties created this unique layout. The table's structure is based on how atoms are built, especially their electrons. Understanding the table's shape unlocks the secrets of chemistry and the diversity of matter. The periodic table is our guide to the building blocks of everything. How are elements organized? It's a question that has puzzled scientists for centuries. Imagine trying to make sense of the world around you. But the fundamental building blocks are all jumbled up. Where do you even begin? What organizing principle could possibly bring order to this chaos? It all starts with the atomic number, a seemingly simple yet incredibly powerful concept. This number is more than just a label. It's the key to unlocking the secrets of the elements and the structure of the periodic table. The atomic number represents the number of protons residing in an atom's nucleus. Protons, with their positive charge, are the defining characteristic of an element. This number dictates the element's identity and its place in the grand scheme of the universe. The periodic table, that iconic chart hanging in every chemistry classroom, isn't just a random assortment of symbols. It is meticulously arranged by increasing atomic number, a testament to the fundamental nature of this value. The journey begins with hydrogen, the simplest and most abundant element in the universe, holding the atomic number 1. It possesses a single proton in its nucleus, a solitary sentinel. Next in line is helium, with the atomic number 2. Helium boasts 2 protons, making it stable and inert, a noble gas that refuses to react with others, and so on, each element claiming its spot based on its unique proton count. Lithium with 3, beryllium with 4, boron with 5, and the list continues, marching across the periodic table. This sequential order dictated by the atomic number is the very backbone of the table's structure. It's the underlying principle that brings order to the elements, revealing hidden relationships and predictable patterns. Before the discovery of atomic numbers, scientists grappled with atomic weight as a means of organization. They believed the mass of an atom held the key, but relying on atomic weight led to inconsistencies and confusion. Certain elements seemed out of place, defying the expected trends. The table felt like a puzzle with missing pieces. Then came Henry Moseley's groundbreaking discovery of the atomic number. Through his work with X-rays, he revealed the true significance of the proton count. This revelation fixed the inconsistencies, clarified the table's logic, and ushered in a new era of understanding in chemistry. The elements finally fell into their rightful places. The atomic number is more than just a position marker. It fundamentally defines each element, dictating its properties and behavior. An atomic number of 6 protons unequivocally means carbon, the backbone of all organic molecules and life itself. An atomic number of 79 protons signifies gold, the precious metal prized for its beauty and resistance to corrosion. This seemingly simple count, the number of protons, is the ultimate determinant of an element's identity and its unique chemical nature. It governs how it interacts with other elements, forming compounds and driving chemical reactions. The table's elegant sequence, stretching from 1 representing hydrogen, all the way to over 118, encompassing the newest synthetic elements like oganesson, is the key to unlocking its intricate design and understanding the relationships between the elements. It's like a secret code, waiting to be deciphered. Arranging the elements by their atomic number reveals the underlying patterns and predictable trends in their properties. Elements in the same column share similar characteristics, making the table a powerful tool for prediction. These patterns are what make the periodic table such a powerful tool for scientists, allowing them to predict the behavior of elements and design new materials with specific properties. It's the very foundation, the cornerstone upon which our understanding of chemistry is built. It's the essential starting point for understanding all the other complex relationships and interactions that govern the world of chemistry, from the simplest reactions to the most intricate molecular dances. The periodic table, in its elegant design, isn't just a random assortment of elements. It's meticulously organized to reveal underlying patterns and relationships. One of the most fundamental aspects of this organization lies in its rows. These rows, stretching horizontally across the table, are called periods. They represent a sequence of elements arranged in order of increasing atomic number, which corresponds to the number of protons in the nucleus of an atom. Each period is read from left to right, starting with elements that exhibit metallic properties and gradually transitioning to non-metallic elements as you move across. This arrangement isn't arbitrary. It reflects a systematic change in the electronic structure of the atoms. The length of each period, the number of elements it contains, is directly related to the arrangement of electrons within the atom, specifically the electron shells. These are the distinct energy levels where electrons reside, orbiting the nucleus in a structured manner. These shells dictate how many electrons an atom can hold at a particular energy level. The first period, the shortest of them all, contains only two elements, hydrogen and helium. This is because the first electron shell, closest to the nucleus, can only accommodate a maximum of 2 electrons. Once that shell is full, a new period begins, and electrons start filling the next shell. The second and third periods are longer, containing 8 elements each, ranging from lithium to neon in the second period, and sodium to argon in the third. This is because the second and third electron shells can each hold up to 8 electrons. As we move across these periods, electrons progressively fill the available spaces in the shell. As you move down the periodic table to longer periods, such as the 4th, 5th, and 6th periods, you'll notice they contain significantly more elements. This increase in length is due to the involvement of more complex electron shells and subshells, which can hold a greater number of electrons. These shells include d orbitals and f orbitals, allowing for a more intricate arrangement of electrons. The period number itself provides valuable information. It tells you directly how many electron shells an atom of that element possesses. It's a quick and easy way to visualize the atom's structure. For example, sodium, which you'll find residing in period 3, has electrons distributed across 3 distinct electron shells. This means that its outermost electrons are in the third energy level. The way electrons fill these shells, following specific rules and principles like the Aufbau principle, is what ultimately dictates the overall shape of the periodic table. It's a direct consequence of the quantum mechanical behavior of electrons, and explains the varying length of each row, from the short first period to the much longer periods further down the table. The entire structure of the periodic table is fundamentally about organizing electrons in an orderly and predictable way, based on their energy levels and the shapes of their orbitals. This underlying pattern is not just aesthetically pleasing, it's incredibly useful because it helps us predict how elements will behave, how they will interact with each other, and what kind of compounds they will form. It's a powerful tool for understanding the world around us. The table's columns are called groups or families. Elements in the same group share similar chemical properties because they have the same number of valence electrons. Group 1 elements, like lithium and sodium, all have 1 valence electron, making them highly reactive. Group 17, the halogens, have 7 valence electrons and are eager to gain 1 more. These similarities make it easy to predict how elements in a group will react. As you move down a group, atoms get larger, but their valence electron pattern stays the same. This consistent structure explains why elements in a group act like chemical cousins. The table's columns group together elements with shared traits. It's a shortcut for understanding chemical behavior. Let's delve deeper into the fascinating world of the periodic table and examine the family traits that define element groups. The periodic table isn't just a list, it's a carefully organized chart that reveals recurring patterns in the properties of elements. These patterns arise from the arrangement of electrons within the atoms of each element. Let's start with Group 18, located on the far right of the periodic table. This group is home to the noble gases, a collection of elements with unique characteristics. These elements are famously unreactive, meaning they don't readily form chemical bonds with other elements. They are content in their isolated state. This lack of reactivity stems from the fact that their outer electron shells are completely full. They have achieved a stable electron configuration. Because their outer shells are already full, they don't need to gain, lose, or even share electrons with other atoms. They are perfectly stable as they are. As a result, they rarely form compounds with other elements. They prefer to exist as individual atoms, floating freely. Now let's shift our attention to the other end of the periodic table, specifically to Group 1. This group is known as the alkali metals. Unlike the noble gases, alkali metals have just 1 valence electron, a single electron in their outermost shell. and they are incredibly eager to lose it to achieve a more stable electron configuration. This eagerness to lose their valence electron is what makes them extremely reactive. As we move further down the group, from lithium to sodium to potassium and beyond, the more reactive these alkali metals become. The intensity of their reactions increases dramatically. This is because their outer electron is increasingly farther from the nucleus, making it easier to remove. The farther away, the weaker the attraction. These trends we observe on the periodic table elegantly explain why sodium explodes so spectacularly in water, and conversely, why helium floats so effortlessly in balloons. The periodic table, in its ingenious design, shows us these patterns at a glance, allowing us to quickly understand the properties of different elements. Understanding these group traits empowers us to predict reactivity and anticipate chemical behavior. It's a powerful tool for chemists and scientists. The table serves as a roadmap, guiding us to a deeper understanding of element families and their unique characteristics. It unlocks the secrets of the chemical world. Hydrogen and helium are special cases on the table. Hydrogen sits above group 1 but isn't a true alkali metal. It can act like a metal or a non-metal and sometimes doesn't fit neatly anywhere. Some tables even place hydrogen by itself or above group 17. Helium, with 2 electrons, might seem to belong in group 2, but it's placed with the noble gases in group 18. That's because helium's full shell makes it extremely stable and unreactive, just like the other noble gases. The table prioritizes chemical behavior over simple electron count for these elements. Hydrogen and helium remind us that nature doesn't always fit perfectly into our categories. The table adapts to reflect real chemical properties. The jagged staircase on the table divides metals from nonmetals. Metals on the left are shiny, conduct electricity, and lose electrons easily. Nonmetals on the right, plus hydrogen, are poor conductors and often gain or share electrons. Metalloids, like silicon and boron, sit along the staircase and have properties between metals and nonmetals. Silicon, for example, is a shiny semiconductor, crucial for electronics. The staircase isn't a wall but a transition zone. This division helps us quickly identify an element's general properties. The table's layout makes it easy to spot metals, nonmetals, and metalloids at a glance. It's a visual shortcut to understanding element types. What about those 2 rows at the bottom? They're the Lanthanides and Actinides. These elements actually fit into periods 6 and 7 but are pulled out to keep the table compact. Lanthanides, elements 5871, are metals with very similar properties, filling an inner F subshell. Actinides, elements 9103, are also metals, all radioactive, and fill a different F subshell. Many actinides, like plutonium, are synthetic and used in nuclear energy. Their similar electron configurations make them hard to separate and give them unique chemistry. The table's design reflects both practicality and the special nature of these elements. It's a reminder that the table is both a scientific tool and a clever piece of design. The periodic table isn't just a list, it's a predictive tool. Mendeleev left gaps for undiscovered elements and predicted their properties with amazing accuracy. When elements like gallium and germanium were found, they matched his predictions perfectly. Today, the table guides scientists in creating new elements and predicting their behavior. It helps explain why sodium reacts with water or why carbon forms so many compounds. The table reveals patterns in reactivity, bonding, and material properties. It's chemistry's ultimate map, evolving as we discover more about matter. The periodic table is proof that science can uncover the hidden order of the universe.